In this video, we're going to take a closer look at limiting values. So we've already talked about limiting values. We've said that a limiting value is what your function gives you in the long run. Like if you plug in larger and larger numbers, if you plug in 10, 50, 100, bigger and bigger numbers, if your function is giving you numbers that sort of start to level off at a certain value, that's called a limiting value. Not all functions do this. Not all functions have a limiting value, but some do. We have seen limiting values in the context of tables and graphs. Let me just go over those real quick. So in a table, right, so let's say we have a variable t, and then the function that depends on t is k. So t is going by 5s, and if you look at the k, right, it's growing, it's growing, it's growing, but it's growing by less and less and less. And actually it goes down right here, but it does seem to be sort of leveling off maybe at around 111 perhaps. So you can see that in a table usually. In a graph, we know what it would look like for a leveling off. In fact, this is where we get the phrase leveling off. We see the graph actually level off to a horizontal line. So the graph could do whatever at the beginning, but then at some point it kind of levels off and either becomes horizontal or kind of gets closer and closer and closer to a horizontal line. And this value right here would be the limiting value. Okay, so as I say, we've seen limiting values in the context of tables and in graphs, but we haven't really seen it in the context of formulas, and that's what I want to talk about in this video, seeing limiting values from your formula. I mean, one thing is you can always, of course, use your calculator and take your formula and create a table and or a graph and see it from that point of view. But there's actually a way in a lot of cases to see what the limiting value is just right from the formula itself. And so let me talk about how that works. First, let me talk about some common formulas that don't have limiting values. So in everything I'm going to talk about, let's assume that my variable is t. Okay, so if you have, and let's say it's I don't know, I'm just making up letters. Let's say v of t is blah blah blah. Okay, so if v of t is just like a number like, let's say like 5t, a really simple formula, right? So we know that this, if you plug in bigger and bigger numbers for t, you're just going to multiply it by 5. That's just going to get bigger and bigger and bigger, of course. So this will grow without bound. And so in particular it has no limiting value. If you had t squared or t to the 5th or t to some power, right? Again, it's easy to imagine just, you know, say with your calculator plugging in 10 and plugging in 20 then plugging in 30, plugging in 100 to either one of these. It's just going to get bigger and bigger and bigger. And it will again grow without bound, no limiting value. We can also do square roots even if you take the square root of bigger and bigger and bigger numbers. The square root cuts it down to size a little bit, but the answers are still going to get bigger and bigger, just kind of slowly. So again, this still grows without bound, no limiting value. Okay. However, if we do, say, like 1 over t. So now, and I mean, you can try this on your calculator if you plug in 1 over 10, 1 over 20, 1 over 30. Because the number that's growing is in the denominator of a fraction, right? That means that that fraction is getting smaller and smaller. And in fact, it's getting closer and closer to 0. So this actually has a limiting value of 0. So the limiting value equals 0. By the way, sometimes, especially when we're working with formulas, although it's not necessarily just with formulas, instead of saying limiting value, sometimes people just say limit. The limit equals 0. Yeah, so it's like it's getting smaller and smaller, but it's kind of not going to drop below 0. It's kind of limited by 0, but it will get as close to 0 as it possibly can even though it never gets there. Okay. So, of course, anything that grows without bound, if you sort of flip it to the denominator, it will now, the fraction will get smaller overall, so the limit will be 0 again. If you're ever in doubt, the goal here is to be able to predict these right from the formula, but again, if you're ever in doubt, you can put it into your calculator, look at a graph or look at a table, and verify that, yes, these numbers are approaching 0. They're getting closer and closer to 0 as you go, like in a graph, as you go out to the right, or in a table as you just go down the table, right? Okay. So we could have something like 4 over t cubed plus 6. And again, you just think to yourself, okay, I'm putting in bigger and bigger numbers here. They're getting cubed, so that's even bigger. I'm adding 6, so that's even bigger. And that's all in the denominator of a fraction. And so that's going to 0. So with formulas, 0 is kind of a pretty common limit or limiting value. Now we could do something like this. What if we had a formula that was 5 plus 7 over t cubed? All right. So again, we argue, okay, t cubed, this is getting bigger and bigger and bigger when you plug in larger numbers for t. 7 over that, though, then is going to get smaller and smaller and smaller. The fraction, right? The denominator of the fraction is going to get bigger, so the fraction gets smaller. So this part of the formula is going to get smaller and smaller and get really, really close to 0. But it's 5 plus that. So the overall answer is going to be getting closer and closer to 5 plus 0. It's going to be getting closer to 5. So the limiting value here would be 5. This part is just going to 0, but it's 5 plus basically something that's really close to 0. So that'll end up being something that's really close to 5. Okay. So this is how we deal with just like t and powers of t. In the numerator, it grows without bound, no limiting value. If it's in the denominator, then it goes to 0. It has a limit of 0. And sometimes that can be embedded in a larger formula, and just that part goes to 0, but then you just figure out what the whole thing is, like we did in this case. All right. What's interesting is when you have a fraction again, but the top and the bottom are both getting bigger. So let's say we have 3t over 5t squared minus 6, something like that. So we're plugging in t, bigger and bigger values for t. The bottom, the bottom again is getting larger and larger. We square it and multiply it by 5. Yeah, we're taking 6 away, but still, if like a bigger number goes in here, this bottom will get bigger. So the bottom is getting bigger. That on its own is trying to make the fraction get smaller, but at the same time, the numerator is getting bigger too, right? Because t goes here as well. So those bigger numbers that we're putting in here, they're also going in here. So both the numerator is going up and the denominator is going up. And so it's kind of like which one wins. Well, I think intuition serves us well here. It does turn out to be true that since this is just a t, but this is a t squared, the t squared ultimately will win out. So this one is going to win out. Even though this is getting bigger, the bottom is getting bigger more, faster, So the bottom will eventually swamp out the top. And this fraction overall will go down, and it'll get closer and closer to 0. So the limit or the limiting value is 0. So it's because we had a higher power of t on the bottom. Now if we had the higher power on the top, 7t cubed minus 5t squared plus 8t plus 3. Okay. So again, the top is getting bigger. T to the 5th, so that's getting bigger. The bottom also is getting bigger. the bottom is mostly controlled by the t cubed. Eventually, when you put in really gigantic numbers, t cubed is going to be way bigger than squareds or just t, or obviously the number 3. So these numbers are almost doing nothing. This guy's in control. It's getting bigger and bigger as well. But it's in the denominator, right? So it's making the fraction get smaller. So again, we have sort of competing forces. The top's trying to make the fraction get bigger. The bottom's trying to make the fraction get smaller. Which one wins? Well, in this case, t to the 5th beats t to the 3rd. Even with these other guys in here, that doesn't matter. Even if I made this a plus, these really are nothing in the long run compared to this one. So it's the bottom is t cubed, the top is t to the 5th. The top will win. And so no limiting value. It just gets bigger and bigger without bound. And it's because the higher power of t was on the top. Okay. Now finally, the last case is, what if they're tied? So what if it's 6t cubed, and down here we have 2t cubed minus 5t plus 11. Okay. So again, top's getting bigger, bottom's getting bigger, but the bottom getting bigger means trying to make the fraction smaller. These guys don't really matter in the long run. It's really t cubed against t cubed. And since they're tied in terms of the power, what you do in this case is you actually just take the numbers that are multiplying them. So we have a 6 and we have a 2. So the answer is there is a limiting value, and it's 6 divided by 2, which of course is 3. So this is when top and bottom are have the same power. Okay, so let me just do another example of this. If we had even if we just had something like this, 3t plus 7 over 5t minus 9. So 3t and 5t, the smaller guys are not going to matter. This one's getting bigger and bigger. This one's getting bigger and bigger. They are tied, though, because they're both t's without a power. And so what you do is the limiting value is the numbers multiplied onto that highest power on the top and the bottom. So the limiting value is 3/5, which is 0.6. And again, verify this. If we were doing this in class, I'd have us do it on the calculator. Plug in really big numbers for t in this formula, and you'll see it's going to be close to 0.6. Or graph this formula, and you'll see, I forget if it'll come from the bottom or from the top, but it'll level off at 0.6, you'll see. So there are ways to check this. You're not totally flying blind. You can use a table or a graph, or just literally plug in some numbers manually to verify that this is the case, and you will see that it is the case. Okay, so I'm going to stop this video now, and I'm going to have a second part to this video, in addition to maybe another video on a second topic, but there will be at least one more video on this topic that you should check out.